Hello, we're Scenarios Group 10, and this is our Scenario Soup presentation.
So, firstly, we dove into the sequence of events that led to the failure of the crane. In 2013, PS Fields Limited had to repair the cranes being used by Hytric cars twice on separate occasions, showing the history of damaging equipment. Also, the installation kit for the crane sent by Red Wings Lift contained no mounting instructions, missing tightening torque values, and the incorrect stud bolts, the M24s rather than the M30s, with one of the 8 missing. Red Wings Lift did not reply to any emails for this information. Mistakes were made when installing the crane as the nylock nuts were screwed into the wrong locations, and they used their own tightening torque values alongside a different stud bolt provided by Mr. Anderson. The overload system was not tested in the inspection of the crane, therefore there was no telling if it was functioning. Overall, these factors led to the crane collapsing.
When looking at the culpability of the parties involved, we decided that only two parties will share the most culpability. One is Hytric Cars and the other one is Red Wings Lift. The reason Hytric Cars shares the most culpability, specifically Mr. Anderson, is because he authorized the use of the crane, even though if it was against regulations and it was not installed according to specification. Also, Red Wings Lift is also held accountable because they delivered the wrong stud bolts to the branch, and they also failed to provide information for the installation of the crane when it was specifically asked by Mr. Anderson.
Since the crane broke at the connection of the plinth and the base of the crane, this is where most of the design critiques must be. This is true because two major faults are identified here. The first one is that the nuts were fitted on the opposite way. The nylock locking nuts should be on top and the standard nut should be on the bottom. Since it's the other way around, it makes it weaker and the bolt more susceptible to detaching. Also, the wrong stud bolts were used at this connection, as the stud bolts of the old crane were used instead of the stud bolts for the new crane. This leads to two issues. Both bolts have different tightening torques. The bolt that was meant to be used, the M30X500, has a tightening torque of 550 Newton meters, and the bolt that was used, the M24X500, has a tightening torque of 350 Newton meters. This means that the bolts would have over tightened. In addition to this, both bolts have different proof loads and different minimum ultimate tensile loads. The bolt that was meant to be used has higher values for both of these measurements. This means that the bolt that was meant to be used can handle more load than the one which was used, and this could be a major factor as to why the crane broke.
The design specification, we considered various aspects of the design and came up with criteria for each aspect. We based the quantitative aspects on common values for similar commercially available cranes, the X+47 itself, online information, and educated guesses. For example, one performance aspect is that it should have a high lifting capacity, and it should be able to lift up to 2 tons without failure. And then to test this, we will do multiple stress tests to ensure that it meets our criteria. Alongside the existing alarm warning system on the X+47, we should have additional safety devices added to our crane. Safety should be the #1 priority during crane operation, and therefore in order to protect the operator, we should use the latest technology that is available to us in order to maximize safety. The internet has given rise to clever ways to operate systems safely. The Finnish company Epic Oy has come up with a Linux-based programmable controller that includes 4G connectivity and helps with digitalization and remote diagnostics, which will lead to a safer and reliable operation of the crane. Currently, this technology is being used in bigger cranes, but can also be used and implemented on our crane model. Other companies are using a system whereby cloud data is used to calculate the ideal lifting route and therefore reducing the input needed by the operator, which will all in all increase safety. Another safety device that we can use on our crane is a system like the AMCS Technologies anti-collision system. This system is able to prevent crane booms, hoist ropes, and hooks from colliding. It can stop the crane moving to areas of the workplace where the crane is not supposed to go. It can calculate distances between components, and it also detects the speed at which the crane is moving. It also has a data log feature that registers all events and so can be viewed remotely, so this helps solve any problems that might come up.
When looking at improvement in design for the new crane is that we can implement an automated override system. This feature helps prevent injury to workers around the crane while working in the crane. And it also prevents further collapse of the crane. More specifically, the boom and the base of the crane. And it uses that, and it does that by using a feedback control loop, which basically it calculates the load that's been lifted on the crane, and if that load is greater or equal to the maximum load that the crane can handle, then the crane stops the function altogether. And this then doesn't prevent it tells the workers that they are using a load which is more than the maximum.
One of the problems with the current design was that the moments experienced by the system would only be resisted by the bolt stud fastenings that held the base panel of the crane onto the plinth. This would put too much pressure on the bolt studs. To solve this, we can improve the design by adding more crane stabilizers to distribute the forces experienced by the system and lessen the loads on the base panel. These would provide additional reaction forces to support the crane and improve its balance and structural stability. We went with a cross-tab formation as it adheres to our design specification. It doesn't affect performance, it's cost-effective, and it can be implemented at a radius of less than 11 meters. It also overall improves the safety of the system.
The direct consequence was that the base panel lost connection with pins, and the main body of cram dropped over due to loads carried on one side only and the corresponding unbalanced transverse moments. Hence, a counterweight could be a solution to prevent the overturning by applying an extra transverse moment to make it balanced. Movable counterweights are commonly added on the counterjib of tower cranes, which is not suitable for our case, with a much shorter boom on the cram. So we just need to ensure that it is attached on the other side from boom. The counterweights applied on the base panel also helps with preventing overturning. For the risk assessment, we have three options, including health and safety executive risk assessment evaluation, fault tree analysis, and failure mode effects critical analysis. Initially, we made the first draft with HSE style based on the materials uploaded, which is purely quantitative and helps us a lot in concluding capability of each failure and the possible improvements for the new design. However, according to the feedback from our last scenario, quantifying as much as possible would help audience understand in a more intuitive way and be persuaded more easily. In our specific case, lots of explanations and clarifies will be necessary. So the purely quantitative FTA is also not suitable, leading us to the final choice, FMECA.
On our FMECA, we divided the crane into 8 components, which had a grab hook, power supply, crane control, lifting chains, base, boom, overload alarm, and the control operating system. After identifying the faults, we first explained each component's function. The next step was to talk about the possible failures in each component. Then, we found what the local effect and the system effects of each failure would be. After that, we talked about how we could detect each failure and how we would fix the problem if it ever arose. On the last step, we had to find how severe the accidents would be if the accident ever happened and how likely they are to happen. To figure these out, we brainstormed and rescheduled the possible outcomes as a group to determine the severity and the likelihood of the risks.